Okay, so let's get started. While you're doing that, all right, here's another reminder. The final exam will be a week from this coming Tuesday, so 2 weeks from yesterday, 7 p.m., PSF 166. I will be posting review materials soon. As soon as they're up, I'll let you know, okay? 2 or more hours. So most of you will be done in a couple hours, but because it's the nighttime and there's no final after us, we can kind of try to stay as long as the custodians will let us, okay? Sometimes the custodians come and kick us out after 2.5 or 3 hours, but we can kind of leave it open-ended in terms of how long you get to take it. But most of you will be done in a couple hours. All right. Another there. Okay, so some of you have heard of this thing called identities. Okay, so in trig, there's something called identities, and so let's talk about what is an identity, and you can understand that by comparing it to what's an equation. So here's something that looks familiar from algebra. So we think of x as a quantity, right? So x could be height or temperature, and x could take on many values, right? That's how we've thought of variables and quantities, that when you assign a variable to a quantity, you're thinking about that letter taking on every value that the quantity could have. So here x, so we can think of x taking on many values, but not every value of x would say make that statement true. And so in this particular case, there's only 2 values of x that make it true. But again, our concept of x isn't just those 2 values. It's any possible value that whatever quantity we've assigned it to could assume. But then you have an equation like this, and it says, okay, x could take on many values, but only 2 of those would make this true. Okay, what about this? So if we take a look at this, if we do a little work on the right-hand side, what do we get? 1/2 x times 6x is what? Isn't that 3x squared? And 1/2 x times minus 8? Minus 4x. So what do you notice here? So really these expressions are truly equal. So x takes on many values. In this one, every value makes the equation true. Let me just do it here. So 1/2 x times 6x is 3x squared. 1/2 x times minus 8 is minus 4x. So the right-hand side is identical. It's just in disguise, but it's identical to the left-hand side. So identical, identity, right? Meaning that now any value of x that you put in this will be true. It will make that thing true. Okay? So identity comes from the idea of that the 2 sides of the equation are identical, and therefore any value of x that you put in makes it true. Okay, so these identities arise because we have all these different relationships in trig. There's just dozens and dozens of identities which are true for every angle. Okay, so here is a familiar picture. Suppose a circle has a radius, any radius of r. So say 46 feet. Okay, so suppose the radius here is 46 feet. I want to use radius lengths as a unit of measure. Radius lengths as a unit of measure. So I want you to label the sides of this right triangle using radius lengths as a unit of measure. So you're asking, how many radius lengths is that right there? How many radius lengths is that right there? How many radius lengths is that right there? Okay? This is review. We should all be able to do this. So my measuring stick is not feet. My measuring stick is a radius length. So let's start with this right here. So my measuring stick is a radius length. What's the measure of that length right there? John, what do you think?
1.
He wants 1. That's it. Yes, it's 46 feet, but it's also 1 radius length, and that's what we're measuring in. Okay, this is the black bold bar down here. No estimations. I want an exact value of radius lengths that this is. Everyone should be able to get this. Everyone knows how long that is exactly in radius lengths. If you don't, you're in trouble. I would guess that your score was low on the exam. Mass got it. He wants cosine theta. Yes. That's our output of cosine. The horizontal distance to the right of the vertical diameter measured in fraction of a radius length. Fraction of a radius. And so this is not even worth asking now. Of course, you all will say sine theta after that. Okay. So now we got this makes a right triangle, right? So here's our first identity. What relationship brings together the 3 sides of the triangle? It's a right triangle. I know these guys know. What will it be? Maria. So she's using the Pythagorean theorem. So this side squared plus this side squared equals 1 squared. And so we write, this is not great notation, but it's very prevalent. So if you square, you're squaring sine theta, this is the notation that's used for that. It's not great notation, but it's everywhere, so you have to be aware of that. This means take the sine of theta and then square that value. Okay? So 1 squared, we don't write 1 squared, you just write 1. So is this true for only some values of theta, or is it true for all values of theta? So if I move my triangle up here. So say I make the triangle here, different value of theta. Okay? And here's theta. Still true or not true? Still true. It's a different right triangle, but it's still, the base is still cosine, the height is still sine, and the hypotenuse is the radius length, so still 1. So, is it true for all values of theta or just some? All values of theta. You have a different triangle, but this relationship holds. Therefore, it's an identity. It's true for any value of theta that you put into it. This is called the Pythagorean identity. It's probably the most widely used, the most common one you'll see. All right, and then in problems, you'll often solve for one of these. So sine squared theta equals 1 minus cosine squared. So that's something you'll use a lot. You'll have sine squared, and you'll substitute in 1 minus cosine squared. Similarly, cosine squared theta equals 1 minus sine squared. Most common one you'll see, the Pythagorean identity. It's true for every angle, and that's what makes it an identity. Questions on that? Okay, next one. So, recall the 2 meanings of tangent theta we discussed. We said there were 2 meanings, so I'm going to come back here and do this again. So this is cosine theta. This is sine theta. This is 1. So one of our meanings was the measuring this right here in radius lengths. The vertical height above the horizontal diameter along the 3 o'clock tangent in radius lengths was what value? So how long is that in radius lengths right there? Tangent of theta. That was the definition we had. In radius lengths, that's tangent. But then we said we had another meaning for it. What was the other meaning for tangent theta? And that was what your homework focused on. Slope of the terminal side. How could we write the slope of the terminal side? Oh, I sure didn't mean to do that. Yeah, so it would be change in y. So the slope of this pink line here. Change in y over change in x. Change in y is? Okay, true for any value of theta. Here's another identity. This is an identity because it's true for every theta that you could pick. Tangent is always sine over cosine because that would compute the change in y over change in x of the terminal side. So it'd be the slope of the terminal side. Another identity. Okay, so cosine starts at the min, midline, or max? Min, midline, or max? Cosine starts at the max. Okay, at pi over 2, it's at 0. At pi, -1. So here's cosine. And now let's sketch if it was coming after or behind by pi over 2. I'll do that in blue. So then at pi over 2, where would it be? If we want a different graph that comes behind this one by pi over 2. So am I going to do pi over 2, I'm going to go here, or am I going to go here if it's behind? A or B? B, starting later, coming behind. Okay, and if I kept going this way, I would be at 0 here. So cosine coming behind by pi over 2 is just the same as what? Sine. So cosine, that's behind by pi over 2. I should have done it in blue. So two ways to write that blue curve. The cosine that's lagging behind by pi over 2, or just the sine. There's another identity. Because that's true for any angle that we pick. So here are the angles on the x-axis. Doesn't matter what angle you pick, you get a point on this curve, and that's cosine of it's lagging behind by pi over 2 or sine. It's true for every angle, therefore it's an identity. Okay, we can do the same thing with sine coming ahead, and we get something similar there. Okay, let's take a look at this. This is kind of a cool one. Let's see if I can find it here. No, not that. No, I saw somewhere here. There it is. Okay, so let's investigate what's called the opposite angle. So looking over here just at the left-hand graph, don't worry about the right-hand graph, so I'll take that off. So what would be the meaning of the angle negative theta? What would be the meaning of the angle negative theta? Yeah, so if you swept an angle counterclockwise of theta, that would be, so like the pink one would be an angle, that's standard theta. Then minus theta would be the blue one. It would be the angle, the same angle swept clockwise. Wow. Okay? So, then what would the sign of the opposite of theta be? So what would the meaning of it be? So if you took the sign of the opposite of theta, how would you define what you're talking about? It's the sign of the angle that gives you this point. Yeah, so it'd be like the vertical distance below, right? If you take the opposite of the angle and take the sign of that, you're going to get. So we're still taking the sign of an angle. So it's still going to be vertical distance above, but how will it compare to sine? That's the question. How will the sign of the opposite of theta compare to the sine of theta? Will it be the same? Same but negative, right? So wouldn't it be true that you could say this? That the sine of this, the opposite angle, is the same as the opposite of the sine of the positive angle. Because one's above and one's below. One's positive, one's negative. Another identity. Okay, what about cosine? How would the cosine of the two angles compare? Equal and opposite? So right here, what's the cosine of theta? What's the cosine of theta? So here's our terminal point. Cosine of theta would mean what? Let's see. What's that? 0.5 radians. So what does it mean? What are you looking at? Yeah, distance to the right of the horizontal diameter. So you're looking at this coordinate right here, this length, to get the cosine of this angle. What about the opposite of theta? Yeah. She's saying it's the same. Is it opposite or is it just the same? It's the same, right? It's the same positive coordinate. Is that true for all angles? Do you see that the horizontal coordinate is the same whether you take the angle or the opposite of the angle? It's not. It's because you're going to you're going to the same place to the left of the vertical diameter. So what's the identity for cosine of opposite of theta? Equals what? Equals cosine of theta. Another identity. So going the opposite way still gives you the same. If you have a small angle, it's still to the right. Once you're greater than pi over 2, they're both to the left, the same amount. So if you take the opposite of the angle in the cosine, you get the same horizontal coordinate that you do just for regular cosine. But with sine, we get equal and opposite, right? Because one goes up and the other goes down. One's above and the other's below. So this is the idea. So we could just keep going for hours and just come up with these relationships that are true for every angle. That's why identities becomes this kind of big deal in trig, because there's so many relationships that are true no matter what angle you pick. So let me put a summary up here. So I'm not going to leave this up long. Take a picture or see the video, okay? But here's the basic ones. We got the Pythagorean. We talked about that one. This is the most common one. We got the shifts we saw in the graphs. If cosine lags behind by pi over 2, it falls right on top of sine. Similarly, if sine is ahead by pi over 2, it's the same as cosine. We talked about the opposite angle identities. Here are some that we did not talk about. Okay, double angle. But sine of twice the angle is equal to 2 times sine of the angle times cosine of the angle. That's a very common one that you use. Cosine of 2 times an angle has 3 different versions. You can see them right here. Cosine squared minus sine squared, 1 minus 2 sine squared, 2 cosine squared minus 1. Here's all our right triangles. So we've learned these. So now there's something called cosecant. Cosecant is the reciprocal of sine. This is not inverse sine. Inverse sine is where we flip the input and output. This is 1 over sine, okay? So 1 over sine is cosecant, and so if it's 1 over sine, then it's hypotenuse over opposite. You take the reciprocal on the triangle ratio. Okay? 1 over cosine is secant. So secant in the triangle is hypotenuse over adjacent, or the reciprocal of it, of cosine's ratio. Cotangent is 1 over tangent. So since tangent was sine over cosine, cotangent is cosine over sine. In the triangle, take the reciprocal of the tangent ratio, so it's adjacent over opposite. Okay, so, and this is just scratching the surface, okay? These are the most basic ones that you should definitely know, but there's many, many more, okay? So one part, let's see here. One thing that's important is being able to work with identities algebraically and manipulate them into other expressions. So sine x over cosecant plus cosine over secant, we can do some algebra on this, and we can come up with a different, maybe simpler form of that. Okay? So here are some techniques. The first technique is change everything into sine and cosine, because that's what we have more identities for sine and cosine. So when you ever have cosecant, secant, and cotangent, and tangent, sometimes it's strategic to change all of those into their equivalent sine and cosine expressions, and then work on it. So that's the first technique. The other technique is, if you're adding fractions or subtracting fractions, get a common denominator and make it one fraction. So those are the two things that kind of come up the most. In addition to that, you just have to know algebra. You just have to know algebra. So in this one, we'll use both of those techniques that I suggested. The first is, we're going to change cosecant to 1 over sine. So we'll have sine over 1 over sine plus cosine over 1 over cosine. So before we add these fractions together, let's see if we can do anything else individually on those. What's sine over 1 over sine? Invert and multiply, right? If you invert and multiply, you just get sine squared. And same thing here. Invert and multiply, you get. So we got sine squared x plus cosine squared x. Is there anything we can do with that? It's just 1. Can't get any simpler than that. So this thing right there, for all angles, no matter what x is an angle here, right? Because it's input into sine and cosine. No matter what x is, that expression is always equal to 1. And we showed it. Okay, so why don't you take a minute and see if you can do these two. And I'll take attendance. So reward you for being here. So algebra is important, but then here's the two things. Change everything into sine and cosine. Create fractions, and then common denominator, add fractions when you can. All right? Those are two prevalent techniques. Times what? Sine over cosine. Plus cosine. So we can do sine squared over cosine x plus cosine x. What can we do with that? Add them with a common denominator. What's the common denominator? Cosine. So we don't have to do anything to that. It's just sine squared. What do we have to do to this to get cosine in the denominator? Cosine over cosine, right? We're going to multiply by cosine over cosine. And then we can add those with a common denominator. So plus cosine squared over cosine x equals 1 over cosine equals secant x. Have a wonderful Thanksgiving. Next homework will be due Wednesday, a week from today. Web work and written.